Welcome back. This is the second installment documenting an experiment in genetic computing and neural simulation. Its goal is to use genetic algorithms in order to evolve and create functional neural networks. Episode 1 talked about some of the theoretical underpinnings for the project. The first creatures evolved were very basic and about as interesting as sponges. This next generation of organisms can move, see, and respond. You can catch up by binge watching at danlovey.com/critter. In order to create and test more complex behavior, there needed to be a more interesting simulated world in which these creatures can move about in, sense their environment, and respond to stimulus. Given the ability to see these obstacles at a distance and hopefully avoid collisions. Later, I will add food and other objects. Just like the previous examples, all the creatures' behaviors have been evolved and run on the same neural simulator described in the first installment. Interestingly, what has emerged quickly is that the details of each of the organisms involved are very different. They seem highly sensitive to the initial random populations. Given the same environment, each lineage seems to have created unique solutions and behaviors. All of the behaviors presented here have been evolved. There has been no direct programming. The motion control and sensory responses are directly driven from an evolved neural network. Let's talk about what these creatures look like and how they work. The critters from the last episode were very simple. They could not move and had a rudimentary ability to sense its environment. Its only response was how wide to open its mouth. Here is the new organism, the guppy, Critis optica. It has a main body 30 units in diameter. Attached to the main body are 6 functional appendages. As before, these are connected directly to the internal brain and act as neurons in the simulation. There are 3 eyes. Each can sense an obstacle 100 units away and will fire a neuron proportional to the distance to that obstacle. The middle eye looks directly ahead, and each side eye looks out 90 degrees. The tail provides forward propulsion. Maximum speed is 20 units per frame. At the base of the tail are 2 turning jets. Each jet can change the guppy's direction by up to 20 degrees. The first guppies I evolved were blind. They could move forward and turn. Hitting an edge meant painless death. I also started each one near the top edge, pointed towards that edge. This forces it to evolve a sharp turn, then a pattern of movement that keeps it alive as long as possible. Each successful guppy evolved its own distinct pattern. Reminded me of different shell patterns. Next, I connected the center eye. As you can see, it does a pretty good job of navigating the obstacle course. The animation lights up the eye red and paints a blue line out to the obstacle it senses. It's interesting to note that it developed a side-to-side wiggle. Many of the one-eyed guppies develop this. Since the field of vision is only 1 pixel wide, it's like looking at the world through a straw. A wiggle gives a little more visual information. This is actually the first guppy I evolved after connecting the two lateral eyes. You can imagine my joyous surprise when the first run succeeded in producing a viable guppy. However, this is a bit of beginner's luck, as not all evolutions lead to success. The fitness function used in the genetic algorithm is simply the distance traveled from top to bottom. Here's another one that has a more complex motion. Turns out that the choice of the previous guppy to go guppy right opens up an easier path to the bottom. The random choice this one made during its evolution sets it on a more difficult path. It has more obstacles to deal with and requires a more complex brain strategy. Much like the wiggle of the one-eyed guppies, three-eyed guppies would often evolve a circular motion. Because the field of vision is still only 1 pixel wide in each direction, going in circles increases the visual information coming in. That's only a theory. It could be a random quirk of the evolutionary model. You can see in the animation when each eye detects a wall and how it responds to that obstacle. It seems to have evolved a pretty effective navigation strategy. Here is the brain of one of the three-eyed guppies in operation. It's surprising how few neurons are required for this behavior. 30 neurons and 100 connections. A few never fire at all. The system currently does not prune unused neurons. 6 of these neurons are connected to the eyes and the muscles, so it does not take that many individual neurons to create behaviors and environmental responses, like the rotifer from episode 1. All of the organisms evolved in the same obstacle course. Here's how they fare when the obstacles are removed. Some have the same basic strategy. Hug the wall, then turn at each angle. Others behave in surprising ways when the walls are removed. Because this trivision guppy evolved to start with a left turn, it races to the bottom corner first.